Section 1.3 is functions and their representation. So we're going to review function notation and look at different ways that we can represent a function and get a formal definition of a function, and look at set builder notation and then identify some functions. So this table right here forms a relation with ordered pairs in the form of month, comma, precipitation. A relation is just any set of ordered pairs. So here we see the average rainfall for the month for Portland, Oregon, and these numbers are paired up in such a way that each month has a single number associated with it that represents the average rainfall. If we denote the ordered pairs by a set of ordered pairs x comma y, then the set of all the x values are called the domain, and the set of all the y values is called the range. To help you keep straight which is which, just notice that these are in alphabetical order. X comes before Y in the alphabet, domain comes before range, so X goes with domain and Y goes with range. The domain would be the set of all of the months, and then the range we typically write in order from least to smallest. We're not writing these as ordered pairs, so we just list all of the Y values from those sets of ordered pairs. So any pairing between two sets of data is considered a relation. A function, on the other hand, is a unique relation where each element in the domain can only be paired to one element in the range. That means that the x values cannot repeat if you have a function. And I've already discussed what the domain and the range is, so I'm going to skip that. The domain of any function will be all real numbers except where the function is undefined. Right now, the only two functions that you have to worry about where a function could be undefined is a fraction and a radical, an even root. If you have a zero in the denominator of a fraction, then that point is undefined because we can't divide by zero. So for example, if you had the function f of x equals x divided by x plus 2, then to find the domain, we set the denominator equal to 0 and solve for what x cannot be. So my denominator in this fraction is x plus 2. I set that equal to 0, and then to solve for x, I need to subtract 2 from both sides. Remember, when you're solving an equation, you can pretty much do anything you want to the equation as long as you do the same thing to both sides of the equation. We get x is equal to negative 2. This is the element that's not in the domain. So when you write your answer for the domain, if you're asked to do this on a test where it's pencil and paper, I'm okay with you saying x is not equal to negative 2. But if you're typing an answer in for your homework in my math lab, they may want you to use interval notation. Are y'all familiar with interval notation? It's the interval that goes from negative infinity to negative 2, union negative 2 to infinity. These curly brackets here denote set notation. That means that every number between negative infinity and infinity except for negative 2 is included in this domain. If you don't include a number in your domain, you put parentheses. If you do include it, you put brackets. We never include infinity because we're never equal to infinity, so infinity and negative infinity always get parentheses. This may make more sense when we look at the next problem. The other way that a function can be undefined is if we have a negative underneath an even root. So for example, I told you that g of x was equal to the square root of 5 minus x. To find the domain for a radical, we set the radicand greater than or equal to 0 and solve for what x can be. Positive numbers are greater than or equal to 0. You have to take the square root of a positive number. You can't take the square root of a negative number. Hopefully y'all remember that from either high school or intermediate algebra. The radicand is just the fancy name that we call this expression that's underneath the radical. So what I'm going to do is I'm going to take 5 minus x, set that greater than or equal to 0, and then solve for x. When I solve this for x, I'm going to subtract 5 from both sides, and that gives me negative x is greater than or equal to negative 5. And then to make the x positive, I'm going to divide this by -1, and what you do to one side you have to do to the other, but because it's an inequality, when you multiply or divide by a negative, you have to flip the inequality, and that gives us x is less than or equal to +5. So the domain for this problem is going to be the set of numbers that goes from -infinity to 5, but I do include the 5 because this is less than or equal to. This expression is written using inequalities. This is the same answer written in interval notation. If you were to graph this solution, we would have a number line, and then we would have a 5 here, and our answer would be everything to the left of 5. So we would put a solid circle there. There's 3 different ways of representing the same answer with a graph, an inequality, and interval notation. You need to be familiar with all of those. How many of y'all have to take calculus eventually? Definitely be familiar with interval notation. The domain for any function is all real numbers except where the function's undefined, and here's the 2 ways right now that our functions can be undefined. Here I ask you to determine which of the following sets of ordered pairs represent a function. State the domain and range of each. It's not just functions that you can find the domain and range for. You can also find the domain and range for just a plain old relation. Remember, the definition of a function says that each element in the domain can be paired to only one element in the range. So does this represent a function? Yes, it does. What is the domain? It's the numbers 1, 3, 5, and 7. What is the range? 2, 4, 6, 8. For part B, does this set of ordered pairs represent a function? What's the domain of this function? 1, 2, 3, 4. And what's the range? Same thing. So what we observe is we still have a function if the x's are equal to the y's. On the next set of ordered pairs, does this represent a function? Oops, I got a yes and I got a no. I have no repeating x value, so yes, this is a function. What's the domain of this function? And what's the range of this function? Just 1 and 2. So what we see here is that the y's are allowed to repeat and still be a function. Does this one represent a function in part D? So this is just a plain old relation. What is the domain of this relation? And what is the range of this relation? So when you have a function, the x's cannot repeat. What I have written in green are the conditions for a function. If you have a graph and I ask you to find the domain and range, what you want to do is you want to look at the shape of the graph. This arrow on the end means that this graph is extending in this general direction beyond the scope of this grid that I have available here. Your domain values are along the x-axis. So this would be our domain. So it's going to go all the way out to -infinity and come back and stop at 1. Our range values continue up forever because this arrow right here is going to the left and up. So our range values will go off to infinity. So the domain of this function in interval notation will go from where to where? Do I put a parenthesis or a bracket on the 1? Bracket because it's actually equal to 1. This graph is touching at 1. What about the range? What do I do for it? Do I put a parenthesis or a bracket on the 0? It goes from 0 all the way up to infinity. We use the bracket when we include the point. We use parentheses if we don't include the point. Remember up here on this problem, I said I used parentheses here because x could not be equal to -2. I did not include the -2, so I put parentheses there. But we said x could be equal to 5, so I put the bracket right there. On this problem, x can be equal to 1 because the graph touches 1 on the x-axis, and y can be equal to 0 because the graph touches at y equals 0. All of that leads up to the vertical line test. Remember, we said that the x's cannot repeat for different values of y. This graph is a function because the vertical line crosses at most one time, any vertical line. This one is not a function because we have 3 points where we have the same x value, -3/2, but the y value here looks like it's at 2. Here's a point at -3/2, -1/2. And here's a point at -3/2, -2. So all three of these points have the same x value, but they have different y values. So the x values are repeating. And we said that if the x values repeat, it's not a function. So that's how we can use the vertical line test to determine if we have a function. We can also represent functions using a diagram. For example, this blue circle here represents the domain. The pink circle represents the range. This is a function because every point in the domain is going to only one element in the range. This one's not a function because of this point right here. That 2 gets paired up with two different y values, so I would have the x's repeating at 2, 5 and 2, 6 if I were to write out the ordered pairs that this mapping illustrates. For this graph I would have 1, 3, 2, 5, and 2, 6, and we see that these x values repeat, so that's why it's not a function. If you have a graph and you want to check and see if it's a function, just use the vertical line test. If the vertical line crosses more than one place, it's not a function. One thing that you can tell whenever you're looking at an equation, if the y is raised to an even power, it's not a function. If you don't have a graph and you don't have a set of ordered pairs, if y is raised to an even power, it's not a function. So is part A a function for y equals x? Does this represent a function? Yes, it is. What about part B? It's not a function because the y value right here is being squared. Your function notation looks like this: y equals f of x. F is the name of the function. We typically use f, g, h for the names of our function until you get into physics, and then we use like v of t, a of t for velocity and acceleration, so that the name kind of means something to us in relation to what we're studying. X is just your domain variable, it's your input. Y is your range variable, it's the output. Functions can be represented four different ways. You could have a verbal representation of a function. For example, multiply x hours by 50 to obtain the distance y miles. Here we would say y is equal to 50x if we wrote that out as an equation. Or we could say f of x equals 50x. That's function notation for this verbal representation. We could also have a numerical representation through a table of values or a list of ordered pairs. We could have the symbolic representation using the function notation, or even a graph to represent a function. So here the graph represents a function because it passes the vertical line test. Each vertical line only intersects the graph one time. We can evaluate functions by replacing x with whatever number is here in parentheses in the function notation. So for this problem, I'm told that my function is equal to x squared plus 2x. The first thing I want to find is f of 3. This function has an x for the variable. That means that everywhere I have an x, I'm now going to plug in a 3. The function says you take something, square it, and add 2 times that thing, and that thing that goes in there is the 3. Then I can just simplify this information and say that 3 squared is 9, 2 times 3 is 6, and 9 plus 6 is 15. So what we would say is f of 3 is equal to 15. You just plug in the number that's in the position of x in place of x. Then we want to find f of a. Remember, your function just says you take something, square it, and add 2 times that thing. We drop in place of x whatever's in the parentheses right here, so that would be a. So we would say f of a is equal to a squared plus 2a. Notice when you put numbers into the function, you get numbers out. If you put letters into the function, you get letters out. And the last thing I asked you to find was f of a plus 2. You can put an expression or even a whole other function inside of a function. That's called composition, and we'll go into greater detail on that later in the semester. So f of a plus 2, I go through the same process, and that's the beauty of mathematics. We don't memorize problems, we understand processes. The process is that x is just a placeholder. We take x, the function says you take something, square it, and add 2 times that thing. Then we just drop in whatever's in parentheses here in place of x in the name of the function. So what I drop in here is a plus 2. Now I can simplify this by foiling this out and distributing that 2, but I'm not going to do it right now. I think we'll come across doing that later on. Do y'all remember how to FOIL? When you square something, you multiply it by itself. I'll go ahead and simplify it. So what we would say is f of a plus 2 is equal to a plus 2 times a plus 2 plus, and I'm going to go ahead and distribute that 2. That would be 2a plus 4. So when I FOIL this out, that's going to give me a squared plus 4a plus 4 plus 2a plus 4, and then I just combine my like terms, and that gives me a squared plus 6a plus 8, and that's multiplied out. We have some practice problems. A function g is defined below. Write g as a set of ordered pairs. We're told that g of negative 4 is equal to negative 6. How would I write that as an ordered pair? What do I write first? Remember, ordered pairs are in terms of x comma y. What would I use for the x value? And what would I use for the y value? Give me another point, and another point, and your final point. Whatever's in parentheses on the name of the function is the x. Whatever that function name is equal to is the y. Second practice problem, I want you to use the graph to the right to complete the following. The first thing I want you to do is find the domain and range. On these graphs in my math lab, assume that there's arrows here unless there's a dot like there is in this next problem. So this is going to go to the left and to the right forever, and it's also going to go down forever. For part A, what would be the domain? All real numbers that go from negative infinity to positive infinity. And what would be the range? Negative infinity to 3. So we put a parenthesis on the negative infinity, a bracket on the 3. Because we're never equal to infinities. Positive and negative infinities always get parentheses. We use brackets when we can be equal to something. This graph is actually equal to y equals 3. And remember, the range goes with the y values. Whenever you're using interval notation, remember to put things in order from smallest to largest. You never want to put 3 to negative infinity. We always go left to right on the number line. Part B says to use this formula to evaluate, or use the formula to evaluate g of negative 1 and g of 1. The formula is this equation right here. We're told that g of x is equal to 3 minus 2x squared. If you're asked to find g of negative 1, we're going to plug in a negative 1 in place of x and then simplify. Negative 1 squared is 1, so that becomes 1 times negative 2 is negative 2, so that's 3 minus 2, and that is 1. So we would say g of negative 1 is equal to 1, and g of positive 1 is equal to what? 1 squared is 1, 1 times negative 2 is negative 2, 3 minus 2 is 1 as well. And then on part C, we're asked to use the graph to evaluate g of negative 1 and g of 1. So looking at the graph, we go over to negative 1, and there's g of negative 1, and we go over to x equals 1 and go up to the graph, and there's g of 1. So our points right here are at negative 1, 1, and at 1, 1, so that means that g of negative 1 is equal to 1 and g of 1 is equal to 1. We're going to do the same thing again. Tell me, what is the domain and the range of this graph? The domain, remember, is the x values, the range is the y values. It looks like it goes from negative 2 to positive 2. Do I put parentheses or brackets there? And then the range goes from where to where? 5 to 2. What do I put, parenthesis or bracket first? And then what? And then what? And then what? You've got it. Now you don't have to worry about writing down these curly braces right here in my math lab. They're already written out for you. They just want you to type in this. Make sure you know where the brackets are because it will count the answer wrong if you use a parenthesis when you should use a bracket. B says to use the formula to evaluate the function. I'm going to skip that step just because it's time consuming. Are y'all okay doing part C and just look at the graph to evaluate and find g of -1 and g of 2? Looking at the graph, we go over to -1, and right there is g of -1. What value is that? 3. And g of 2, we go over to the graph where x is equal to 2. We go up to it and we end up at this point, and that's going to give us what? 6. Wait, 1, 2, 3, 4, 5. It is 6, which means this answer right here is wrong, isn't it? What should it be? It should be 6. I was trusting you guys to count. Here's another problem that's similar to one on your homework. It says use f of x to determine verbal, graphical, and numerical representations. For the numerical representation, use a table with x equals -2, -1, 0, 1, and 2, and evaluate f of 2. Here's the function f of x equals 3 minus x. Determine a verbal representation for the function. Select your correct choice below and fill in the answer box with your choice. So there's 4 choices to choose from for the verbal representation for this function. I'm not going to read them all to you, but you read them and tell me if you can see which one you think should be the right answer. Do we multiply x by a number? Do we subtract the input of x from a number? Do we divide the input of x by a number? Or do we add the input of x? We subtract. So our answer is going to be this one right here. We subtract x from what? That's what goes right here. This says in words what this says in symbols. Then we want to determine a numerical representation for the function by completing a table. Oops, all of a sudden I changed functions. We're going to work with this function now for the y value. I think I may have accidentally clicked another problem whenever I was making these notes. So we're given the x values. How would I find the y values? Just plug it in. What's 5 minus -2? 5 minus -2. What do you get when you subtract a 2? You add, it's going to be 7. What's 5 minus -1? What's 5 minus 0? Okay, can y'all see the pattern? 7, 6, 5, 4, and 3. Then we want to choose the correct graph of this function right here, 5 minus x. Well, that means that I'm graphing y equals 5 minus x, and I'm plotting these points. If you recall from your intermediate algebra or your high school days, when you have a negative number in front of the x on a linear equation, that means you're going to have a decreasing line. So we can automatically throw this one out. That also means that our y-intercept is 5. So this one's not it. That one might be it. It looks like its y-intercept is at 5 and it has a negative slope. This one's not it because it's not decreasing. That's decreasing, but the y-intercept is wrong. So it's going to be B through process of elimination without ever graphing anything. I'm using the fact that the line is written in the form y equals mx plus b, where b is the y-intercept. For this problem, that would be 5, and m is the slope. For this problem, that would be -1. So there's a graph of a line with a y-intercept of 5 and a slope of -1. Then we want to evaluate f of 2. Well, my function was f of x equals x minus 5. So f of 2 will be equal to 2 minus 5, and f of 2 then is -3. Does the graph below represent a function? If so, identify the domain and the range. Does this represent a function? Why not? It doesn't pass the vertical line test. So we would say that the graph does not represent a function, and then you would select that the graph does not represent a function so you don't have to give the domain and range. However, that's for my math lab. For me, I want to know, can you tell me what the domain and the range of this relation is? Because relations do have domains and range. The domain of the relation is what to what? Parenthesis or bracket? -1 to infinity. And then the range of the relation, perfect. It goes all real numbers from -infinity to +infinity, because these endpoints here are slightly going up and down forever as they're also moving to the right forever. Some of this you just need to be able to envision. And this wraps up section 1.3.